Hello, I thought we'd start out with a little bit of a review, identifying the type of lever 1, 2, or 3. So some of these we've seen. Start out with the first one up here. What's in the middle? So the output force is right here, the input force is right here. That makes the fulcrum in the middle. So the fulcrum is in the middle, that makes it a type 1 lever. Let's look at the crowbar here. So what's in the middle? Okay, what's at the end? So we got the output force here on the nail. We've got the pivot point here, so that's the fulcrum, and then the input force would be over here. So what's in the middle would be the fulcrum, which makes this one also a type 1 lever. Here we've got the bottle opener. And we identify what's what. So let's see, here we've got the fulcrum, here we've got the output force, and here we've got the input force. So the output force is in the middle. That makes it a type 2 lever. Here we've got a fishing pole. So let's say that the fulcrum is right here, the input force is right here, and the output force is right here at the tip. What's in the middle is the input force. That means it is a type 3 lever. Here we've got a I don't know what this is. It's some kind of device to lift something up. So it looks like this is the output force, what you're trying to lift. This looks like this is where you apply the input force, and the fulcrum would be here. So the fulcrum's in the middle, which would make that a type 1 as well. Here we have a shoehorn. This one's a little trickier. I would say that this is the part where you stick in your shoes. The pivot point would be down here. Your heel would go here, which would be your resistance force. This would be, this isn't a shoehorn, this is a bottle opener. Well, if it was a shoehorn, and this would be where you apply your input force. So if it was a shoehorn, so I would say it would be a type 2 if it was a shoehorn, but it's also type 2 if it's a bottle opener. All right. So mechanical advantage of 4. This might be a multiple choice question. I might ask you something along these lines of, if an ideal pulley has a mechanical advantage of 4, how much rope do you need to pull to lift resistance of 2 meters? Well, if the mechanical advantage of 4 means it's going to multiply your force by 4, but it means that it's going to reduce your distance by 4. So if you want to lift the resistance up 2 meters, that means you're going to have to pull 4 times that much rope. So you'd have to pull 8 meters of rope, something along those lines. Okay, so on to the main topic is efficiency. So for an ideal machine, the work out equals the work in. We don't lose any energy as heat because there's no friction. So in the real world, though, there typically is going to be some energy lost due to friction, and I represent the machine as this box. So here's the input work that we supply, here's the output work that comes out as output work, and then here's what we lose as heat. So 10 joules of work goes in, 10 joules comes out, but only 8 joules comes out as useful work. So this would have an efficiency of 80% because we got 8 joules out where we wanted it for the 10 that we put in. So 8 divided by 10 times 100 would give us 80%. So this is the equation for efficiency. Percent efficiency equals work out over work in times 100%. You might want to make a note of this equation as well. I usually abbreviate efficiency as percent EFF, just as we abbreviated wout and win. So give you a second for that. Okay, so if a machine is 75% efficient, that means that for every 100 joules of work that you put in, you get out 75 joules as useful work. Okay, which means that the remaining energy's got to show up somewhere. That 25 joules has got to show up somewhere, and it's going to show up as heat. Okay, for an ideal machine, your work out equals your work in, so you have an efficiency of 100%. Another way to calculate percent efficiency is by dividing your AMA by your IMA and multiplying by 100%. So that is another way to calculate efficiency. Okay, so let's look at a simple example here. So in this case, our fin din equals our FOUT DOUT. We have an efficiency of 100%. But in the real world, because we've got to overcome friction, we have to apply a little bit of extra input force to overcome friction. Okay, and how is that going to affect everything else? Well, we'll see in just a second. So a lever is such that the input force, the effort side is pushed down 2 meters with a force of 3 newtons. A 4 Newton load is lifted 1 meter. What's the efficiency of the lever? Well, the equation is work out over work in. So work out is the output side, 4 newtons times 1 meter. That's our work out, force times distance. And divide that by our work in, which was the input force times the input distance, which is 3 times 2. So 4 divided by 6 gives us, times 100, gives us 67%, 66.7%. Okay? So using a machine which is 20% efficient, how much work will have to be applied to a machine to lift a 10 Newton weight up 2 meters? Okay, so the efficiency is 20%, it says that, so that we put that in for percent efficiency. The work out is we wanted to apply 10 newtons of force to lift an object up 2 meters, so that we want 10 times 20, that's 20 joules of output work. We're looking for the input work, how much work will have to be applied to the machine. Okay, and then there's the times 100. So if we solve this mathematically, we'll get that the work input equals 100 joules. Okay, so back to the slide we were at before. We're going to have to apply a little bit of extra input force to overcome friction. And we want to ask, how is that going to affect some of the other things? So because I had to apply a little bit of extra input force, does that affect the output force? Well, that's the weight of the object I'm trying to lift, so that's not going to be changed. Okay, did that affect the input force? Sure it did. I had to push it a little bit harder. Okay, did that affect the input distance that I had to push? No. Okay, I'm still going to have to push it so far to get it to lift up on the other side so far. Okay, so the only thing that's affected as far as fin din, FOUT DOUT is the fin. Okay, okay, now, how is that going to affect our mechanical advantage? How is this friction going to affect our mechanical advantage? Well, mechanical advantage, actual mechanical advantage, is FOUT over fin. Okay, now if my fin gets bigger on bottom, that means I'm dividing by a bigger number, which means my mechanical advantage is going to decrease. Okay, so friction reduces our actual mechanical advantage. Okay, how does this increase in fin affect our ideal mechanical advantage? Well, that's din over DOUT. Well, din wasn't affected and DOUT wasn't affected, so IMA won't be affected either. Well, which makes sense because that's what we should get if there was no friction. So adding friction won't affect what we should ideally get if there was no friction. Okay, so no change. How will this increase in fin affect our work input? Well, if my force input increases, that's going to make this side of the equation bigger, which is going to make my work input bigger. So I'm going to have to do more work in with friction than I normally would, or than I would without friction. How does friction affect the output work? Well, FOUT and DOUT weren't affected, so my work out isn't going to be affected. So there's no change. How is this friction going to affect my efficiency? Well, you don't really have to go through all this logic to answer this question. How is friction going to affect your efficiency? It's going to make it decrease. But continuing the logic that we were moving through, we know that we're going to have extra work in. Okay, that's going to make this bottom part of the equation bigger, which means we're dividing by a bigger number, which means it's going to make this smaller. So our efficiency is going to go down. Friction makes our efficiency go down. That should make sense. Okay, so what I want you to do is do the back of 7.2.5 now. And that's it for the notes for the day.